We often describe falling in love as a mystical, uniquely human experience, an emotional destiny that exists outside the bounds of biology. Yet early-stage romantic love triggers the same neural pathways as chemical addiction. It functions as a biological trap, overriding conscious choice with a survival mechanism. To observe this clinical reality, researcher Helen Fisher used fMRI to monitor the brain activity of 30 participants in the early stages of a relationship while they viewed images of their partners. The scans revealed a physiological surge. Dopamine activation increased by 180% compared to neutral stimuli, while heart rates rose from an average of 72 beats per minute to 88. This arousal originates in the ventral tegmental area and the nucleus accumbens, regions of the brain explicitly dedicated to reward prediction. These areas create a chemically driven feedback loop. The brain identifies the partner as a high-value reward and releases dopamine to reinforce the behavior, a process identical to addiction pathways. These neural patterns suggest that early love is a temporary neurological high. It prioritizes reward-seeking over emotional stability, creating the intense craving often mistaken for a deep bond. If love is built on stability, logic suggests that certainty should make the feeling stronger, but the biology of reward indicates otherwise. Researchers tested this using a reward prediction model, showing participants images of their partners at unpredictable intervals mixed with neutral stimuli. The results were counterintuitive. Dopamine spikes were 25% higher during unpredictable intervals than during predictable exposure. This aligns with reinforcement learning. When uncertain, the brain generates a reward prediction error, amplifying the signal to ensure the behavior continues. Consequently, emotional intensity reflects the brain's reaction to neurological uncertainty. A stronger feeling is often just a biological response to an unpredictable reward. As a relationship evolves, the brain transitions from this dopamine-driven obsession toward a bonding state governed by oxytocin. Longitudinal data shows that couples spending over 20 hours a week together see a 40% drop in dopamine activity over 8 weeks, while oxytocin-related signals begin to climb. This rise in oxytocin correlates with increased feelings of trust and physiological calm. The frantic energy of the early stage is replaced by stable attachment. However, this creates a specific failure point. The initial chemical obsession often fades before the new oxytocin-based bond is strong enough to sustain the relationship. Researchers suggest this neurochemical transition failure is a primary cause of relationship collapse, as the brain interprets the loss of the dopamine high as a loss of connection. In this system, the cooling of passion is a biological requirement for bonding, even if the individual perceives it as a failure of the relationship itself. Stability can be reinforced through neural synchrony, a state where heart rate variability and EEG coherence align between partners during shared activities. Engaging in shared rhythms, like taking a walk or solving a problem, increases this synchrony by approximately 30%, strengthening the bond at a neurological level. Yet even highly synchronized couples break up. The system destabilizes when emotional expectations and reality clash too frequently. When prediction errors accumulate beyond a certain threshold, the brain reclassifies the partner. They are no longer a reward source, but an uncertain variable to be avoided. To understand the full process, we view love as 3 interconnected loops: dopamine-driven attraction, oxytocin-driven bonding, and cognitive evaluation. Behavioral therapy uses this framework to stabilize the system. Using structured novelty to re-engage dopamine and shared goal setting helps balance these neural patterns. These measurable neurochemical processes reveal that love is a dynamic biological system, continuously rewritten by experience and subject to its own chemical transitions. By identifying these specific phases and failure points, we can apply behavioral interventions to stabilize the bond against the very biological fluctuations that create it.